Thanks, everyone. It's early for a Sunday morning, so hoping the caffeine kicks in here. Working on it. Well, I gave a version of this talk at the New York R conference about a little over a month ago, and that was only a 20-minute talk. This is a 40-minute talk, so there's a little more content here, and can go a little deeper into some of these topics. So yeah, we'll have some time for questions at the end. So I've spent the last number of years building some version of DataFrames or tabular data interfaces. So this is a bit of a meta talk about all the DataFrame interfaces and what we can learn from them. Maybe what are some of the problems that still exist. You would think that in 2015 we wouldn't still be having problems with infrastructural problems with tabular data, but we do, and so it's worth talking about what those are and what we the community can do about them and how we can work better together. Of course, there's lots of opinions here. I do work for Cloudera now. There's a whole story there, but it's we're working for a bigger company, so. These are my opinions and not necessarily the opinions of Cloudera, so keep that in mind. And it's definitely a nuanced discussion, so I haven't really stated anything here as fact. I think there's definitely shades of gray with like all of these issues, and I think you should keep that in mind when giving consideration to any particular item. Probably a lot of you are familiar with my background. I started working on the library that would become pandas in April 2008. I was working in quant finance at the time, so I was really interested in doing analytics and doing data analysis in Python, but there really wasn't. It was this chicken and egg problem where no one was doing data analysis in Python. At least Python was really successful for scientific computing and numerical analysis as like a MATLAB replacement, but it hadn't really gotten any traction in statistical computing, or when people say data analysis on the West Coast, it more means like structured data manipulation, like tables and SQL queries and all that kind of thing. So Python really hadn't been used for all that kind of thing, that sort of stuff. Like interacting with SQL databases was just not on the scientific Python community's radar at that point in time. I spent a few years in finance, took some time off to work on open source, wrote my book, which probably a lot of you own, and I decided to take a break from earning income to make the Python data ecosystem more viable. So I don't think we're completely there yet, but it's certainly a lot better than things were looking in 2010. I started a company with Chang Shi, who's one of the early pandas contributors, and was a former colleague of mine. We worked on that for a couple of years, and we now work at Cloudera as of October. It hasn't been all that long. So a data frame, as you're probably all aware, is what I call a table-like data structure, and it varies a lot from library to library. But you can data frames are more of a user interface than they are a data structure. So there's plenty of tables that exist in the wild that people don't think of as data frames, or the way that you interact with them is quite a lot different than the code that you would see writing in R or writing in pandas. There's a lot of different ways that people look at these tools. So I'm going to talk quite a bit about the internals of the data structure and how that impacts things. But there's the API, like the code that you actually write to interact with the data, ends up being one of the most important factors. Because underneath there's just some bytes and some columns, either in memory or on disk. And the thing that sets the libraries apart is, first of all, is it easy to express your computations? Can you write down in a succinct way like what you want to do with the data, whether that's building a model or doing some analytics or doing some data transformation, whatever the task you have at hand. Like if you're spending all your time just figuring out how to express, getting from point A to point B with the data, and that is really hard, then that's a problem with the library. But beyond that, there's a lot of just implementation issues of how fast, how much memory does the library use, the DataFrame library, how fast are the operations, and those can impact you as well. So it's kind of like there's like a hierarchy of needs of data analysis. Like, does the code work? Like, is it nice to use? Is it fast? Does it run out of memory? Like, these are all like really critical matters. Can you read the data that you have on disk? Really simple things like just being able to read the CSV file that you have in front of you is really important. So the meta trend that I see going on with the general data ecosystem is what my term for it is the great, the decoupling, which is to say that, in the past, data systems were very integrated, so you'd have all of the things in one place. You'd have a completely a walled garden kind of implementation where you'd have your API and you have your storage and your computation all in the same library. And the problem with this is that it makes code sharing hard. And you start using pandas or you start using R or any table library, and you're kind of locked in a way because all of your code is very specific to the implementation and the low-level design of that library. And so if you want to switch over from one tool to another, you're a little bit stuck. Like, you have to rewrite your code. There's a bunch of problems there that I'm going to talk about. But one of the really great things about this decoupling that I see happening is the data is getting bigger. So that means that the storage problem, you're not going to want to deal with terabytes and petabytes of data. You want to let somebody else be responsible for that distributed storage problem, and all of the fault tolerance and high availability and replication, all that stuff. The problem of, I have some CSV files on my hard drive. For small and medium data problems, that's completely fine. But if you're dealing with, as they say, big data is largely medium data collected over time. So you might have medium data on any particular day, but if you wait long enough, you're going to have big data. And you don't want to have to deal with that storage problem as a data scientist. There's the other question of the data is getting bigger, and it's more complex. And implementing analytics and making it fast and correct is tedious, and it's a lot of work to make a lot of the analytics fast. And so you would like for the work that happens to make the code fast, and to make it correct, to make it well tested. You would like for as much of that code to be shared amongst the broader data science community as possible, so that we aren't getting into this. I'm going to talk some more about this, but I think one of the symptoms that we see is the language wars, unfortunately, which really are kind of counterproductive, given that we're all in this together. We're just trying to be better data scientists at the end of the day. I think there's a lot of work to do. My prediction is maybe in 10 years, life will be better, but there's a lot of work to do to get there. And over the years, I've become really opinionated about how to build data tools. There's different schools of thought. Some developers who have more computer science. I don't really have a computer science background. I have a math background, so I think about the world in terms of composability. I like to write theorems and then prove things and create lemmas, and then you kind of compose them all together, and then you can prove something really interesting by composing a bunch of pieces together. And it's quite a lot like building software. And so if you design your systems to be composable and to fit together nicely, then you can build up something really nice from this kind of pyramid of abstractions that all fit together in a nice way. And a lot of computer scientists feel the same way, and approaching a data problem, saying, what are we doing at a high level? Let's break that down into small components, and then we'll fit them all together, and then that will implement a system that can solve a problem. But what gets lost in that process is often the usability aspect of not eating your own dog food nearly as much, and stopping like every time you build a thing, you say, well, is this easy to use? If I switch from this function to that function, do I have to look at the documentation to remember how things work? Are the argument names consistent? Is the way that you write the code from step A to step B internally consistent? And I think one of the big things that's happened between now, looking at today versus, 5, 10 years ago, is that I think there's now general consensus in the, the R and Python communities that this kind of usability problem is a real problem and one that merits, thoughtful consideration. If you look at, all of Hadley Wickham's libraries in the R ecosystem, they're well implemented, and they're one of the big benefits of dplyr is that the fact that it's fast. But the thing that's really special about it is the fact that it's internally cohesive and it presents like a nice flow to work with the data that's very productive. So I also think that you as a discerning data scientist who are evaluating software that somebody else has built, when you pick up a new piece of software, you might ask yourself, well, how do I evaluate this? How do I know whether or not this is trustworthy and whether I should be, more or less betting the mortgage on a piece of software? And I think that and you can ask people, like there's this social proof thing where, if you see somebody that you trust using a piece of software, you say, oh, well, so-and-so's using, such and such company is using this software, and if it were bad software, they wouldn't use it because that would be irresponsible. But a thing that you can do that is easy is just to look at the tests and to see, first of all, like what is the development team, what is their approach to testing? Is it a bunch of special cases kind of tossed into a big file? Is there a systematic approach to like how systematic is the approach to testing and ensuring the correctness and performance of the code? Performance often doesn't get tested, and that's unfortunate because often performance is tested in production, and you only find out that the code has been made slower after you've already cut a major release, and that might require, it'd be nice if with every change that's made to a code base, if you had like a very precise view of like how that impacted the performance of real-world, downstream use cases. And I'm sure it's happened to all of you that you upgraded a library and found your code gets slower. There's nothing really more frustrating than that. And diagnosing that is very difficult. Can be very difficult. So as I was saying, the big issue that we have right now is this coupling amongst, I guess, let's call them these 5 key areas. The API, the code that you write, how the data is laid out in memory, so that's the low-level details of the data structure. So when you have a data frame in R, for data scientists, I would say that these really should not be your problem, and these are the things that you don't want to think about, but I just want to raise your awareness about them. But the way that the data is actually laid out in memory makes a big difference. It affects everything downstream, how everything is implemented, how fast it is, how much memory it uses. So it's certainly an issue. A thing that's not talked about as much is how data is serialized and deserialized. So if you're not familiar with the serialization term, serialization just means conversion to and from some other format that can, usually can be read by others. So whenever you read a CSV file, that's, people call that deserialization. And writing a CSV file is serialization. And there's good reasons for writing CSV files, and there's really good reasons to not write CSV files. There's the question of the actual computation. How is that implemented? And that, of course, depends on the prior items. And then kind of a softer issue is how the code that you write relates to how it's evaluated. So when you write a statement, is it immediately executed? Or is there some like optimization system that rewrites your logical data expressions into a more efficient format? And one of the big issues right now is that code sharing is difficult, and for a number of reasons, and as a result is really not happening. And so I wanted to talk a little bit about the in-memory data representation issue, that if you write an algorithm against a data frame, there's several things that it relies on, and I listed them out here. So first is like how the data actually lives in your computer's RAM. So if you have a column that contains numbers or contains strings, depending on the library that you're using, the programming language, you might have a column that looks like an array of strings, but those strings may not be next to each other in memory. They might be pointers into some other part of memory. They might be all contiguous, next to each other in memory. It's an important factor. There's the question of the type system. So if you have a string, if you have a number, how is that physically represented in memory? If there's some support for missing data, how is missing data handled between all of the data types? And then how is memory allocated and deallocated? In particular, how much control the developer has over memory management has a big impact on all of the code that he or she writes. And because all these libraries have developed organically, including pandas, and so I have myself to blame for some of the forward inertia, which is now like almost impossible to change. That there was never like any design effort in the community, like the R and the Python people never got together and said, how can we build a better data frame? How can we share code? How can we make our data and our implementations more interoperable? And the biggest downstream symptom that you see is the fact that you get into a lot of benchmarking and a lot of like published benchmarks about the software that's being built. And even building software with the intent of just creating a better benchmark, which is really unfortunate. And so I think there's like a saying in computer science, for any given set of systems, there is a benchmark such that one of the systems will come out on top. And so whenever you see a benchmark published in which like a particular system wins, you have to really look at like the benchmark. It's kind of like this, like, with statistics, you have the problem of multiple tests, where it's like you have a hypothesis, and it's like, well, just keep coming up with tests until you find one where the p-value is less than 0.05, and then publish that one, because that's not disingenuous or anything. Same thing applies to benchmarks. So probably if you have 3 systems and somebody has like a developer has the system that they're building, they might have a bunch of test cases, and there might be either inconclusive results or not very favorable results, and they'll pick the benchmark that makes their system look the best. So whenever you see a benchmark, please ask questions. It really is and I've been guilty myself of publishing benchmarks, and so I've gotten caught up in this as well. It's really hard. So, but the things that get tested the most are reading and writing files, and generally like reading data into memory, which is kind of unfortunate. You'd think that would just be a solved problem by now. Like, we can read the data into memory really fast. But the other kind of analytics that end up being bottlenecks in analysis tend to be the joins and aggregations. And so basically you're getting this smorgasbord of testing all of the things. That's not only the quality of the algorithm, but you're also can end up bottlenecked on lower level issues that are maybe outside of the developer's control. So just to give you an example, this is like really, a really simple example, but yet like these are the kinds of benchmarks that get published. Is simple, a simple group by, where you group by one column and you compute some aggregate function. Like you want to, so I wrote out the SQL to make it super clear. Like we're summing B for each distinct value of A within a data frame. And so if you break this down into like what's actually happening when you run this code, so the first thing is that all of the values in A and B are being scanned. And so when I say scanned, I mean all of the memory that's associated them is being accessed. And so that might be that if the data is not all stored in the same part of your system memory, it might involve a bunch of like reads from different parts of your system RAM. And so this is very impactful in both Python and R, because if you have an array or a column of a data frame that contains strings, those strings are not stored in, generally speaking, in the same place. So if you're looking at a string in one slot of a column and you want to look at the next string, those are stored often in completely different places in memory. So the system is having to basically look all around your RAM to like pull out those strings and then to compute something with them. So if you had all of the strings kind of stored end to end like dominoes in a contiguous chunk of memory, it'd be a heck of a lot faster. But that's often something that's just not in your control. So the values of A, depending on what type they are, the usual way that this kind of algorithm is implemented is using a hash table. So you hash the value of A, you use that to compute a category ID. So you're testing how fast is it to hash the values of A, how fast is your hash table implementation, and then once you compute that categorization for each value of A, you actually have to sum the values in B, which again involves the scanning of the data in B, and then putting all of the data into a result data frame and returning it back. Data types are also a big thing. I shouldn't need to say, it's kind of an empty statement, but you have all your primitive value types, and most of us, including Python, Python and R, most of our world is in the primitive value type land. But if you're dealing with data that's coming out of the web, you might be dealing with more complex data types. And so I broadly put these data types into kind of the lists, structs, and maps bucket, and I'll explain exactly what those are. And so here's like an example of a chunk of JSON data, which might have come from your favorite web framework, and you have a bunch of this data for all of the people that use your website, say, and you want to do some analytics on this data. So I wrote out like here's what the JSON looks like, here's what the effective table schema looks like. So I wrote that the row itself, each row in the table is a struct, and so struct is just like a dictionary with some fields and types. So name itself is a struct where it has a first and last field, which are strings. Age is an int. I have some favorite numbers, and that's a list of integers. And addresses, C, is something more complex because you have a list of structs that all have a city and state associated with them. And so any given person in your data set will have lived in multiple addresses, and those are all contained in this addresses list of structs. And I didn't really know what kind of an interesting map to put here, but I just put one with some strings as keys and integers as values. And so if you think about like a data frame, like this is a perfectly reasonable schema, but in practice, like this kind of data is really hard to work with in a data frame. And the way that if you're in R, you're in using pandas or any of the data frame libraries, the first thing that you would do if you had a big file containing data looking like this is that you would flatten it out into either one big table or a bunch of tables, and you would duplicate the data in the addresses table, or you duplicate the data in like the name, age, and numbers columns. But if you want to do analytics or you want to count things going into those, say if you wanted to say compute the number of people for whom 2 appears in their list of numbers, that becomes like a more complex operation that's going to be both hard to express and slow. The memory layout, I probably don't need to tell most of you, makes a big difference in performance. And for doing analytics, the best-in-class memory layout is what's called columnar layout, which is that any column in a table, all of the data is stored together in memory, so in a single stripe. So here's a representation of a columnar table. Each color is a different column, and columnar is nice because suppose you have a really wide table with like 1,000 columns, and you're only interested in 2 or 3 columns for a particular operation. That's really fast because you can access those 2 or 3 columns without having to touch any of the other data in the table. So if you're just summing the values within a column, it's going to be super fast. Another thing that's nice is that projections, which is to say, if you have a 1,000 column table and you want to select a subset of the columns, like 5 or 10 columns, you can do that without copying any data, and it's really fast. You can add columns without having to do any copying. Now, the downside of this is that if you have an operation which involves just a single row in the table, that's going to be slow because you're walking all over memory to pick out the values within a single row. And if you want to add rows onto the end of the table, you're also having the same problem of having to walk all over memory to put the values in each column. So the row-oriented approach is basically the opposite of all of these things. It's slow for analytics. Projections are expensive. It's easy to add rows, but if you just have an operation that involves a single record, you've effectively already laid out each row of data alongside each other, and so you can do an operation that involves a single row very quickly. So talk a little bit about the serialization problem. Kind of break this down into text formats and binary formats. And unfortunately, in data science, a lot of our data that we're dealing with is CSV files. I don't really have the statistics on it, but it's like CSV or JSON, probably in over 50% of cases, which is really unfortunate. But part of the problem there is the fact that binary data formats there are many of them. There's no consensus on like what is the best binary data format to use to give data from one colleague to another or one organization to another, and so everyone just defaults to CSV files. Or maybe like a database dump. That's also like a popular route, effectively a text format that can insert rows into a MySQL database. So the problem with text-based formats, well, the good thing is that you can take a CSV file and anybody can read it. The downside is that they're very expensive to read and write. If you don't know the schema, finding out the correct schema is both slow and you can get it wrong. Even if you know the schema, you have to check it when you're reading the data because values might not parse correctly. So there's no guarantee that the file that you've received is well formed. It's also true with binary formats, but at least with binary formats, you hope that the person used a library that has been tested and is correct. And I guess I call text formats is not like high fidelity, so you can lose data as soon as you write it out. And that includes, like with CSV files, the biggest thing is you lose precision, you can lose type information. And if you have like JSON data, you can't put that in a CSV file, you have to store it in JSON. And reading and writing JSON is really expensive. Right. Binary data formats are nice, however, library support for them is really weak. So one of I work at Cloudera, so I have a horse in this race in that we developed Parquet format for use in Impala, which is a high-performance SQL engine. There's another columnar binary format called OrcFile, which is used by some other Apache projects. There's some other projects which are similar to Google's protobuf library, like Avro and Thrift. That are not designed for analytics, but also can transport well-schemaed binary data. The biggest issue is if you're using R or using Python, you probably don't have a reader-writer for these formats, which is really unfortunate. And the reader and writers are inconsistent from project to project, and they can often be a little more difficult to work with than just a CSV file. And you just want to write like read.csv or read_CSV. On the subject of the data representation, if you look at R and pandas, they're actually quite different, and they're similar but yet different. And part of the issue is that in R, you're working within the R type system, which is a simplified primitive value type system. So you have strings, which are called character arrays. You have numbers, you have integers, and you have floating point numbers. You have Booleans. You have a way to store missing data that's very specific to R. But if you're dealing with data types that go outside of the core, like primitive R types, Like if you have JSON data, with nested type schemas, like structs and maps and so forth, it becomes a lot more difficult. Pandas has the exact same problem, so this problem hasn't been solved well in Python either. And missing data is a big problem as well, which I will talk about. So both R and Python use special values to handle null or NA values. And the problem with this is that, and it's one of the big regrets that I have about pandas, is that the missing data handling was, it tries to be as similar to R as possible, but there's some rough edges, and it's working within the context of NumPy. So, we kind of did the best that we could with the tools that we had at the time, and we were going for compatibility with NumPy, and NumPy has no built-in support, at least at that time, had no built-in support for missing data. I don't know what the status on that is. I haven't really paid attention, but we did the best with what we had. But databases, and in the most general case, the best way, in my opinion, to deal with missing data is just to have an extra bit or byte that you carry around where you say whether something is null or not null. You pay a memory use and performance penalty for that extra byte, but in exchange you get a very simple way to track whether something is missing or null, regardless of the data type. So you don't have any type-specific null handling. So the big picture is that I'm actively, as in day to day, working on addressing some of these infrastructural issues, and if they affect you or if they're important to you, I encourage you to get involved in the conversation. And it's certainly more than a one person or a one company job, and will require a lot of people to get in a room and agree, develop consensus about ways to solve some of these questions so that we can share more code and we can all be more productive. That being said, things are pretty okay right now. The R stack, as many of you know, has gotten a lot better. dplyr and what I call the Hadley stack has really transformed the R programmer's workflow in the last couple of years. Other great DataFrame-based libraries. Not everything's great in R. The things that I see as problematic are the type system, the fact that it's not as easy to reuse memory as it should be. So there's relatively easy things that you can do that will cause a whole data frame to be copied and duplicated in memory. dplyr is really nice though, because if you look at it, it's really using the characteristics of the R language to build kind of a new SQL in a way. Like it's a domain-specific language embedded within the R language that has an in-memory compute engine that will work on in-memory R data, but you can also take dplyr expressions and run them in SQL databases. So if you think about kind of talking about that decoupling of let's separate the user interface from the compute and storage, dplyr is doing that, and that's pretty great. Spark is very similar in this regard. Spark has a DataFrame interface now and is very much in the same vein of a decoupled user interface that uses the Spark compute and storage engine and gives you a workflow that is more familiar for an R or Python user. There's some little things like you look at how DataFrames are actually implemented. There's the Spark remote distributed data set, robust distributed data set abstraction, which is effectively a sharded array of row objects, and I don't believe it's represented in a columnar way. So there's definitely ways in which Spark SQL and Spark DataFrames could get better performance from columnar data layout. Pandas has been around for years, but certainly not the ultimate data library, but it's a very, very good one, in my humble opinion. The internals of pandas objects are actually very complex. If you go digging, what's inside a pandas data frame, you might be surprised at what you find inside. And there's very good reasons why things ended up that way. But there's also the organic growth issue that I think the only time that we really took serious time to evaluate the internal details of pandas was in the summer of 2011. And I was working very independently at that time and didn't have a lot of people to consult with. And I had a very particular set of use cases that I was interested in optimizing the performance for. And that led to, an internal structure which now in 2015 seems a bit anachronistic, or whatever's the term, dated perhaps. Like if we went and redesigned pandas from the ground up, there would be a lot of things that come out differently. On the other hand, there's good things about pandas that are very different from any of the other data frame libraries, like the hierarchical indexes, which many of you have probably used, is a very distinct feature from other packages. And the fact that pandas was developed within a financial setting led to really good time series tools. But it really strikes me as unfortunate that a lot of people are choosing Python and choosing pandas for its time series functionality. I think that we should have just as good time series functionality in all languages, that it shouldn't be this sort of secret sauce that's only available in pandas. Things about pandas that aren't as great, on this general topic, is the fact that storage and memory representation type system were from day one all the domain of NumPy, and that led to some of the rough edges and things that we're still dealing with today. And the fact that some of the complexity of the library, which makes it very powerful, can be a source of some pain for people that just want something that feels like an in-memory database table. And because the internals are complex, there's no C API. So if you want to write some low-level code that interacts with a pandas data frame, it's actually pretty difficult. There's some really cool stuff going on in the Python community. There's a new project called Blaze. I think there's some developers from Blaze here at the conference, I think. It's built by Continuum. Continuum folks are here, and it's very much in the domain of the decoupled future. And Blaze is neat because it has one data expression API, and it has many different execution backends, including pandas and SQL. It does not have a native backend, so Blaze isn't addressing some of the infrastructural issues that I've been talking about. But it has a richer type system called DataShape, which is a standalone Python component that you can use. So that's great. I think having a native and full-featured backend for computing expressions on anything that can be expressed with the DataShape protocol would be really great, and I hope that we get there. There was a project called, I guess I shouldn't talk about it in the past tense. It's still being developed, but it's called libdind. It was a kind of a new NumPy project that I don't think is being developed anymore, but was originally intended to be a backend for Blaze, but I think that the things have gone off in a different direction, and it's possible that it could get picked up and become a full-featured backend for Blaze, which would be really interesting. But it does implement that DataShape protocol, so it's one example of a pure C++ library that implements a richer tabular type system. It's all written in C++. Another neat project for Python programmers is the bcalls project, which is an outgrowth of both CArray, a compressed array library, and BLOSC, which is a really nice compression suite that handles bigger tables that can be interacted with as though they were in memory. Got to give a shout out to the Julia project, which has its own data frame implementation, a lot more similar to R than Python. So if you're a Julia programmer and like fast code, and you should check out Julia's data frames as well. It's still early on, which means that an individual could get involved in this project and have a pretty big impact, building it out into a more full-featured library. And there's data frames in all the languages, and so that's great. That I think the general trend has caught on. One of my former colleagues from AQR, Adam, he hopped from a couple of financial firms in New York and built data frames in both Scala and F#, which is pretty cool. And there's even data frames in Haskell and Go and many other and so forth, other languages. So I'm running out of time, hence I'm sort of speeding through slides. But the big thing I wanted to stress in the talk is that figuring out how to share code amongst the data science community. And I think there's been, with all the language wars, it's created like division and like unnecessary like barriers to collaboration amongst the community. And I think if we can figure out how to build DataFrame software that can be used amongst all the data science languages, in particular Python, R, and Julia, that I see as the big challenge for the next 5 or 10 years, and figuring out how those languages can interoperate with the big data ecosystems. That's like Hadoop and Spark. And that's the essential matters I see for bringing about this kind of decoupled future in which you aren't as tied to a particular programming language. You can interoperate between programming languages and collaborate better as developers and better as data scientists with each other. And the other big thing is, of course, the fact that most of the data that's being thrown off and warehoused is JSON data. And if you don't have a type system which can accommodate the data that you're collecting, you're going to end up spending most of your time transforming data from nested form to flat form in order to do analytics. And an extraordinary amount of compute cycles are being used right now just transforming data from one format to another. And that seems like a big missed opportunity to me. So that's all I've got. And thank you for coming.